Welcome back to easy concept. The moment of finish of semicircular section about its center of gravity parallel to x-axis. About center of gravity parallel to x-axis. So the moment of inertia about ixx. So this is the CG. Okay. So here this is a very simple question, but the challenge is to remember the formula. So there was a semicircular section. This is the CG point. CG they said. Parallel to the CG IXX. They are asking what is the IXX. So we know that IXX for semicircular section about the base, which is equal to, we know that the answer is 0.11 r power 4. Okay, 11 r power 4. So this is the answer, but they given in terms of diameter. Therefore, 0.11 into d by 2 the whole power 4. After solving, you will get 0.0069 d power 4. So the option here is B. So this question is actually simple, but the task is whether we know the formula or not. Okay, so keep this in mind. Next one. This is a very interesting question. The principle of impulse momentum techniques. The initial momentum plus impulse is equal to final momentum. This is the theorem. Okay. Okay, that is a, we can say impulse. The concept of impulse is equal to the final momentum of an segment, final momentum minus initial momentum. So this is the final formula of the impulse. The impulse which is acting on a particular element is equal to final momentum minus initial momentum. Okay, therefore this is the theorem. So you can take it as option A is correct. Okay, next one is. Next question. I'm going to give the question here because this question wouldn't be able to finish because this question is a diagram. So that's why I'm going to give this question. The question is the shear stress distribution. The shear stress distribution across a symmetrical I section. A symmetrical I section is given by. A symmetrical I section is given by option A. There was I section. A symmetrical I section. Option B. Option C and option D. So first of all, we have to draw first option. And for the second case, this is the option which is given. 1 minute. Okay. This is the first one. This is the second one. And option C. Option C. So there was a diagram. Okay. This is the diagram. Option D. Option D. The diagram is something like that. Okay. So it's a very simple question. The answer for this question is A. For I section, this is the diagram. I'm going to give some of the diagram so that you will get some more idea. Okay. See, the shear stress distribution is directly proportional to 1 by width. By using this concept, we can draw the flanged sections. Okay. For flanged sections. So for example, for I section, if the width is more, shear stress is less. If the width is less, then shear stress will be more. For I section, the shear stress distribution is here width is more, therefore less. Shear stress is less. Now there is a width is suddenly change, therefore the shear stress is suddenly increase. And here in a rectangular section, we know the shear stress is distributed as a parabola. Then for H section, for example, for H section, the shear stress distribution is, see here width is less, therefore shear stress distribution is more. But at this point position, your shearing stress is less. Why? Because width is more. Therefore, it will be something like that. Always this is the parabola. This also parabola. This also parabola. Okay. Then for L section, the shearing stress distribution is, now how it looks. The shearing stress distribution for this is, we know here width is more, therefore very less. Then suddenly it increases, then you will get something like that. This is the shear stress distribution. Then for a T section, how the shearing stress distributes. For T section, the shearing stress distribution is, here width is more, therefore less magnitude. Width is less, suddenly it change here, therefore this is the diagram. Okay. And for square section, the shearing stress distribution is something like that. For triangular section, this is the shearing stress distribution. For circular section, okay, so I can write here, for circular section, the shearing stress distribution is this one. For hollow circular section, the shearing stress distribution is same, parabola. Okay, so this is the important points that you have to keep in your mind. Okay. Now, the weight of a hollow shaft shall be calculated using. So this is a weight of a shallow shaft. We know that weight is equal to what? Volume into density. Volume of hollow shaft 5 by 4, outer diameter minus inner diameter square. Area into length. You will get a volume. Volume into what is the density? Rho g. It's a very simple question. That is a basic question. So answer for this question is here. Next one. The tangential or shear stress on an oblique plane theta to the cross section of a body which is subjected to a direct tensile stress sigma. Okay. This is the direct tensile stress sigma is acting. and they are asking what is a tangential or shear stress. We know that this is the normal stress and this is the shear stress tau at an angle theta. They said, which is having an angle with respect to sigma. Shear stress on an oblique plane at an angle theta to the cross section of your body. Cross section of your body. This is the cross section of body at which the direct tensile stress is acting. Now we know this formula, right? Tangential stress is what? Tau is equal to sigma x divided by 2. But here sigma x equal to sigma in this sine 2 theta. So now answer for this question is this. Okay. Okay. The next question is, bulking of sand is defined as A. The mass of the sand in a given volume. B. Rodding of sand so that it occupies minimum volume. Increase in the volume of sand due to moisture which keeps the particle apart. Presence of air bubbles that increase the volume of sand. So here answer is bulking. Okay. Bulking means increase in volume due to moisture which keeps and the particle apart. Okay. Which keeps sand particles apart. See, the definition of this is bulking means when dry sample of sand is slightly moisture and dumped loosely then its volume increases relative to its dry volume. This increase in volume of sand is found up to a water content of 4% to 5%. So up to a water content of 4% to 5% and corresponding increasing volume is 20% to 40%. Okay. See, in the dry sample, if you add a water by an amount of 4% to 5%, then there was a increasing volume that was found, that is 20% to 40%. And moreover, if we increase the water content beyond this 4% to 5%, then instead of increasing the volume, it will decrease its volume. Okay. So the bulking only happen up to a water content of 4% to 5%. After that, the decrease in volume will be happen. Okay. So this is the question. Now we can see next one. Addition of fly ash or ground granulated blast furnace slag in the concrete composition may be taken into account. So the addition of fly ash in the concrete composition may be taken into account cement content and water cement ratio. So we are adding fly ash to replacing the cement content. Okay, so we know that the some ratio 1:, for example, 3:6. This is for M10 concrete. This for M10 concrete. In that, this is cement, this is fine aggregate, and this is coarse aggregate. Okay, what will do if you add a fly ash, then the proportion of cement content will be reduced. Okay, or we can say in order to reduce the cement content, we will add a fly ash. Okay, this fly ash means which is getting from the furnace. Okay, so the answer for this question is with respect to cement content and water cement ratio. Next question is, an RCC beam not provided with shear reinforcement may lead to failure in its bottom inclined roughly to. Okay, so there was a RCC beam. Let us consider a beam, and the main reinforcement is used, but there is no shear reinforcement. Okay, that means there is no stirrups. Then we are having a concrete. So this is the thing. Now, if you see the shear force diagram, you will get is something like that in nature. You'll get something like that. Now, you know, the shear crack will be developed with respect to horizontal is 30° for RCC. So if you draw a free body diagram at this point, so consider a point somewhere here. Okay, somewhere here. Okay, then if you draw the free body diagram at this point, then you will get a diagram, free body diagram. At that point, there are two stresses are acting. One is a shear stress, another one is the bending stress, because this is the bending moment diagram. At that point, there was a bending moment also. Okay, because of this bending moment, there was a tensile stress. So this is sigma x, and this also sigma x. Now, in this case, the maximum shear stress, okay, that means the failure plane. The failure plane that was found is something like that. Okay, this failure plane is approximately, we can calculate this, approximately we will get 30°. Okay, so this angle we are getting a 30°, that is a failure is happening around 30° for RCC. But in the PCC, this angle will be around 45°. Why this is the crack angle will be more? Because there is no reinforcement here. Okay, PCC means there is no reinforcement, simply we are having a concrete. Okay, simply we are having a concrete. So in this case, the failure is happen at an angle of 45°. Approximately, this is 45°. Okay, in this case, this is the shear force diagram, and this is the bending moment diagram. Take a point somewhere here and try to analyze this. If you analyze this point, then you know this is the shearing stress. Okay, this is shearing stress, and this is the bending stress sigma x, and this also bending stress sigma x. And here there was a failure which has happened in the PCC is around 45°. After analyzing this, you will get the failure is around 45 degrees. Okay. Now next question. The effective span of a simply supported slab is. So answer for this question. So it's a distance between center of bearing, then the clear distance between the inner face of the wall plus twice the wall thickness, clear span plus effective depth of the slab, distance between the outer faces. So the answer for this question is A. That is sorry, not A. Answer for this question is C. Clear span plus effective depth of the slab. Okay. So here I can give the value for simply supported beam or slab, or simply supported slab, simply supported beam or simply supported slab. For this case, L effective, which is equal to minimum of LC clear span plus D, or center to center distance between the support. Okay, center to center distance between the support. Therefore, this is a simply supported beam. Okay. And from this center point, from center to center distance, we can call it as L effective, or the inner span. Okay, distance between inner support, that is LC, that is a clear span plus effective depth D, whichever is minimum, is a simply supported beam or slab L effective. Okay, so simply supported beam or simply supported slab, the L effective is calculated a minimum of clear span plus effective depth or center to center distance between the support. So in this, option A also looks correct only, the distance between the center of the bearing. So this is the center of the bearing, this is the center of the bearing. So this also maybe looks correct only, but best option is clear span plus effective depth of the slab. Okay, so answer for this question is C. But anyhow, this question is not that much fair. Okay, uh, we can conclude the A also a correct, but I'm giving the answer C is correct. C is correct, but this question is somewhat vague in nature. Okay, next one. Soil liquefaction may occur due to high shear strength of the soil. No, if the shear strength is high, then the liquefaction is not happen. Okay, now liquid limit of the soil is less than 35%. Then weight of the soil particle finer than 0.005 mm is less than 15% of the dry weight of the soil. Option D, both B and C. So the answer for this question is high shear strength of the soil is not correct. If the shear strength is high, then the liquefaction is not happen. Okay, but answer for this question is D. How? Let me explain. So generally the liquefaction will be occur for fine sand and silt. Okay, now see points. Let me give some of the points. Okay, so first point, let me give loss of shear strength, due to cyclic loading is known as liquefaction. Okay, the loss of shear strength due to cyclic loading is known as liquefaction. And one more statement let me give. Loss of shear strength due to upward seepage is known as boiling or quicksand condition. So this is important. Okay, now the liquefaction is happen generally fine sand, generally coisenless soil. Okay, now see, let me explain this. Let me justify B and C is correct. So for example, type of soil and the liquid limit. Okay, type of soil and the liquid limit. That is, first one is a gravel. For a gravel, what is the liquid limit? 0. For a sand, liquid limit is 0. For a silt, liquid limit is 30 percentage to 40 percentage. Then for a clay, for example, alluvial clay, the liquid limit is around 40 to 150 percentage. Okay, now if the liquid limit is more than this 35, then you are having a clay. In the clay, the liquefaction is not occur. Why in the clay the liquefaction is not occur? Since we know that the shear strength is equal to C plus sigma n tan phi. Because of this cohesion quantity, the liquefaction won't be happen. Whether the normal stress becomes 0, the C won't be 0. Because of C won't be 0, the liquefaction is not happen, the clay is oil. But the liquid limit is less than 35, then automatically it comes under silt, sand, gravel, so on and so forth. So in these cases, generally you can find the liquefaction. Okay, so this kind of soil, generally you can find the liquefaction. Therefore, answer for this question B is justified. Then what is the C? So justification of C is, generally the classification of soil, generally the percentage of fines. That means percentage of fine means 0.002 micrometer. Okay, 0.002 not micrometer m. Size is 0.002 m. If the size is 0.002 mm, less than 12 percentage, then classification of soil done by mainly CU and CC. What is CU and CC? CU is the coefficient of uniformity. CC is the coefficient of curvature. Okay, so these two are only holds good for coarse grain soil. But if percentage of fines greater than 12 percentage, then classification of soil done by mainly plasticity chart. Plasticity chart meaning liquid limit and plasticity index. So this plasticity index mainly for clay soil. So if the percentage of fine is greater than 12, then we can conclude the soil is having clay particle. If the percentage of fine is less than 12%, then we can conclude the soil is having coarse grain particle. That means the clay particle domination is less. So if the clay particle domination is less, then it is subjected to liquefaction. In this case, the clay particle is more than, that is clay particles domination is more. Therefore, the liquefaction, influence of liquefaction here is less. Okay. So that's the thing they said. The weight of the soil particle is finer than. So instead of this 0.002, they given 0.005. Anyhow, this 0.005 is less than 0.002, right? Therefore, this condition is called criteria here. Is less than 15%. So instead of 15%, our case is general case is 12% of dry weight of the soil. In these two cases, the liquefaction will be happen. Okay. So option for this question is D. Next one. In the design of tension member, okay, the length of the connection can be reduced by using lug angle. It's a very simple question. In the design of tension member, the length of the connection can be reduced by using lug angle. Okay. So let me give some of the points regarding the lug angle. Lug angle is a small piece of angle used to connect outstand leg of tension member to the gusset plate. Okay. Next point, lug angle reduce shear lag effect and to reduce the length of connections, and it will reduce the length of the connection to the gusset plate. The next point, if we use lug angle, then resultant reaction and resultant action passes through the center of gravity of main angle. So if you use a lug angle, then the resultant reaction and resultant action both are passes through the centroid of the main angle. That means coincides to each other with the main angle. Okay. Then, so let me draw the diagram so that you will get some more idea. So this is the gusset plate. Okay, gusset plate, and this is your anchor. Okay, and this is the main angle, and this is the lug angle, and this is main angle, and this one is lug angle. And the thing is, these two are connected. This is the outstand leg of main angle. This is the outstand leg of lug angle. These two are connected by a bolt. And minimum number of bolt which is used to connect outstanding leg of lug angle and main angle is 2. Very, very important point. Minimum 2 bolts are required. Minimum 2 bolts are required to connect outstanding leg of lug angle and outstanding leg of main angle. Okay, so this is also a factual data you have to keep in your mind. Okay, this is all about the lug angle. Okay, the next one is the lateral torsion buckling will occur. So the lateral torsion buckling means, see, suppose there was a beam. If the beams are not supported laterally, the supports are not supported laterally, then what will happen? There was a twisting which will be happening along this direction. Okay, so in this direction, there was a twisting will be happened. Okay, now see, lateral torsional buckling will occur in beams which are laterally unsupported. If these are laterally unsupported, so in this direction or this face from this face and from this face is not laterally supported, then automatically there was a buckling or torsional buckling will be happen. Therefore, answer for this question is this one. And you know the IS 456 2000 gave the lateral stability of beam. IS 456 2000 gave lateral stability of beam. One, laterally supported at the ends only. Then laterally supported laterally unsupported. The length should not greater than minimum of 60 B or 250 B square divided by D. Second one, for a cantilever. For a cantilever, L unsupported should not greater than minimum of 25 B or 100 B square divided by D, whichever is minimum. So this is the data which was given by IS 456 2000. So keep this in your mind. In the upcoming examination, maybe you can expect this equation itself. Okay, this formula itself they will ask you. Okay. Now next question is very interesting question. Biaxial bending occurring. Answer for this question is a purlin. Purlin is a beam element which was used to support the roof truss. Sorry, that is the roof cover. And this purlin is subjected to biaxial bending. Okay, tension member is not subjected to any bending. Beam is maybe subjected to biaxial bending or not maybe subjected to biaxial bending. And boom means what? Boom is a compression member used in cranes. Okay, therefore best option is A. And some more point let me give. Purlins are designed as a continuous beam. That is something like that. Is designed as the continuous beam. And the Bendiment diagram for this is something like that. So this is the Bendiment diagram. This is a positive Bendiment diagram. This is also a positive Bendiment diagram. So this is negative, this is positive, and this is positive. Okay. And M max, which is taken for design, is equal to WL by 10. So this also they will ask you. Okay, this question which was asked this year IES. Okay, the purlin which is designed for a maximum bending moment of WL by 10. Okay, so this also important point that you have to keep in your mind under purlin. Okay, now anchor bolts to resist overturning moment are used slab base. First question is when the column carries axial load and moment. When the column carries axial load and moment, then the anchorage bolt. What is anchorage bolt? Anchorage bolt is a bolt which is connecting. Anchorage bolt is a bolt connecting column to the footing. Column to the footing through bearing plate. Bearing plate. And this anchor bolt, it is subjected to tension force. Okay, it is subjected to mainly tension force. If there is a overturning moment, if there is a eccentric load which is present, then it will create a overturning moment. That overturning moment also resisted by the anchorage bolt. Okay, anchorage bolt to resist the overturning moment are used in the slab base when the column load carries axial load and moment. That means when a column carries axial load and moment, then anchorage bolt resists the overturning moment. So this is the column. Okay, suppose your load is some eccentricity, and this is the, for example, bearing plate, and this is the footing. Okay, now this is the plate, and this is the footing. And this is the plate, bearing plate. This is the bearing plate. Okay, here the column, this base plate is connected with the footing by using a anchor bolt. This is the anchor bolt. Okay, so these two are anchor bolt. So generally this anchor bolt is subjected to tensile force. Okay, suppose if there is an eccentric load, if there is a load just acting somewhere here P, then it will create a overturning moment PE. We can analyze this load as at the center P axial load and the moment P into E. Okay, this eccentric load we can analyze P and P into E. Now this P into E, which is create a overturning moment. Okay, so the anchor bolt to resist this overturning moment. Okay, to resist this overturning moment, when the column carries axial load and moment. So this is the column. This column now carries axial load P and moment PE. Because of this PE, there was a overturning moment. This overturning moment also resisted by this anchorage bolt. Okay, so that's the thing. So anchor bolt to resist now overturning moment when the column carries axial load and moment. If the column carries only axial load, that means the concentrated load, then this anchorage bolt only carries axial load. Okay. If there is eccentric loaded column, that means if there is any moment, then the anchorage bolt also carries that moment. Okay. Now, next one. In a highway bridges shall not be considered to be carrying any live load when the wind velocity at deck level exceeds. If it is exceeds 130, then we will not allow any live load. Okay.